Let's begin. Welcome again, everyone. Hope you're having a good day and a good week. If you have your name tags, please put them in front of you. I know I promised to get you nicer tags, but apparently I forgot to place that order. Things related to old age and stuff like that. So I'll remember to get those. Try to get those today. Your homework too has been assigned, and most of you are already on the second problem, which we will touch upon today, but I think you would know how to do it. We're going to solve a similar problem in class today. And lectures are being posted on the YouTube channel as fast as I can export the recording, and each recording is like 4 or 5 gigabytes. So it takes a minute to export it, convert it, and then I edit it a little bit and try to cut off if we're taking a break, cut out of the video so you don't waste your time sitting on YouTube, and upload those. So it takes a couple of days sometimes. Sometimes I do it very immediately. If it's not posted on the Canvas front page, always make sure you're subscribed to the YouTube channel, and then you'll get an alert when I post something over there. So that's the fastest way to get to the latest recording is on the YouTube channel. And again, there's a ton of resources on the Canvas files directory. Feel free to explore those. There's, resources and additional reading material. If you're confused about something or you want to enrich your learning, go ahead and explore those, and feel free to ask me about those as well. There's no need to take pictures or do recording in the class. I guarantee you the slides are top quality PDF on the Canvas page. The audio and video recordings are near Ultra HD in resolution. So just sit down and relax and listen to me and focus with me here. Today we will continue on looking at relative approximate error. So this chapter, typically I would cover this entire chapter in one lecture, an hour and a half. It doesn't need much more than that. However, I spread it over 3 or 4 lectures because I use it to demonstrate to you and introduce you to the necessary programming concepts that we're going to need for the rest of the semester. But once we're done here, we're going to go fast, going to get much faster. Okay, so that's why it's important you repeat the exercises we do in class. You listen to every word I'm saying. You try to be in my mind how I'm thinking about things, whether I want to do a for loop, a while loop, slicing an array, defining a routine. I told you last time this is pretty much almost 50-60% of what you will need. Today we will look at some plotting along with a while loop. So that gets us most of the way of what we really need to do numerical methods. The rest is critical thinking and planning problem solutions. So how can we use approximate errors in practice? We recognize so far that relative approximate error seems to be the best measure of error that we can use in practice to assess the validity or to assess our numerical methods. Because in the absence of truth, of knowing the truth, exactly the best we could do is compare a supposedly better approximation to a worse approximation and see where the worse approximation lands. And if it's acceptable, typically the worse approximation is sometimes cheaper. And so we might employ that because it's computationally cheaper. All the exercises we're doing here, you're going to tell me, they're so cheap. It doesn't matter. They take us a fraction of a second to run on our laptop. And I agree with you. You're not wrong. But the context here is when you want to scale these calculations for something like machine learning, building neural networks with billions of data points, any fraction of a second that you could save in a calculation that you might have to repeat billions of times is going to result in a difference between taking 1 hour to compute something or a day to compute something, okay? So think of those in the context of large-scale calculations, which you will hit at one point in your career. And you're going to be taking statistics with me next semester. I'm designing the course right now, and I'm hoping by the end of that course, we're going to be dealing with a very large data set, and we'll show how expensive it can be doing even simple algebraic manipulations on those data sets. Now, in practice, the relative approximate error is actually built in your calculator, and most functions that you use to compute things like sine and cosine and logarithms and exponentials, something very basic. Because like I said last time, any calculation, if you think about it, any calculation has to be narrowed down to something we can do very simply, like addition, multiplication, division, or subtraction. How do you compute the exponential? Like, what is e to the 2? Right? So you have to express that in terms of addition and multiplication, or something that is very elementary that we can do. Any of those functions have to be expressed in those terms. So this is where the Taylor series comes in pretty handy. I created this graphic last year. I went on DALL-E and I said, make a drawing of a Taylor series taking over the world. And the idea here is that the Taylor series, if you've learned about it or not, I'm gonna introduce it a little bit later in more detail and more rigor. The Taylor series is an infinite series. It's a summation that expresses an exact mathematical function in terms of a polynomial, x squared, x cubed, x to the fourth, which is easy to calculate, but it's an infinite sum. Okay, so it could take over the world if you want to do the infinite series. So we're going to stop it from taking over the world using relative approximate error. So the idea is that this vast majority of numerical methods consist of repeated calculations that follow a formula, right? X to the power n over n factorial, or minus 1 to the power n, x to the power n over n factorial, and so on. So the classic example, again, is this Taylor series. For example, the sine of some number x is expressed as this infinite series, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on, for any value of x. Obviously, the more terms you add, the more accurate you're going to get, and that's been proven by math. Okay, we don't take that for granted. This is a series that's going to converge to a value, to a finite value, and that series, the more terms you add, the more accurate you are. So we know that with more terms, you get better approximation than with less terms, but the fact is that this is still an infinite series. Similarly, the exponential function is given by this nice polynomial, 1 plus x squared over 2, and so on and so forth for any value of x. Okay, and then the question is, how can we use this to compute a number in practice? To get a number up to a certain number of significant figures. So that was your homework assignment, problem 2. Today I will cover the background behind that homework assignment. And the idea is, first we want to write a Python code that uses the Taylor series to evaluate the exponential function down to an error of 1%. Okay, so how can we stop this Taylor series from taking over the world if we want to compute e squared or e cubed, okay, or e to the 1.5? And obviously, we cannot add all the terms, but how many terms do you add? 1, 5, 17, 1,000 terms? How many terms do you add? And the number of terms depend also on the exponent. E to the 50 is a much larger number than e to the 0.5. And you'll probably need less terms in computing e to the 0.5 than e to the 50. Okay, so how can you tell what that number of terms is? You can arbitrarily pick a number and say, yep, I trust this. And then I will ask you, what is the error in that calculation? So we're going to invert the logic and say, let's keep adding terms until our error is less than some tolerance, we call it. 1%, 5%, 10%, 0.1%. Okay? Your calculator defaults to some value when you're evaluating e to the e squared or e cubed. It defaults to some tolerance that they built in, and it just computes that Taylor series, and it keeps adding terms until it hits that error. Now, what is that error? Is it a true error? Is it a relative true error? Is it a true error or an approximate error? What do you think? Yeah?
Relative approximate error?
Yeah, because we don't know the true value, right? We're trying to compute a value. So the error in calculating this, if we want it to be less than 1%, that error has to be a relative approximate error. Okay, so how are we going to define the better approximation and the worse approximation? Remember, the approximate error is a difference between a better approximation and a worse approximation. So what's going to be the better approximation? The one with more terms, and the one with less terms is going to be the worse approximation. So we start with one term. Okay, great, that gives us our baseline. Then we add the second term. The one with two terms minus the one with one term, that gives us an approximate error, right? And then 3 terms minus 2 terms, and then 4 terms minus 3 terms, and so on. Okay? So that sets the stage for how you're computing the approximate error. Okay? You can download this notebook if you want. You don't have to. We're going to build it together. We will build it together. And so here's the strategy. And again, in this chapter, I'm going through details of kind of problem-solving strategy and how I would think about the problem, how you should plan your solution. But as we go in the class, we're not going to see this anymore, this detailed explanation of how to approach these problems. So we will define a Python routine. Say, this exponential Taylor is going to take an x value, because we want to be able to compute the exponential up to the exponential of any number, okay? So it's going to take this x value and a tolerance that you specify. So we say I want to compute e squared down to a tolerance of 1%, okay? And you determine whether this tolerance is in percent or a fraction, however you design that, that routine. X is the point at which you want to evaluate e to the x, and the tolerance is maximum allowed relative error. We're going to initialize a variable to keep track of our result, because we're going to be adding terms, 1 plus x squared over 2, and so on. So we need a variable that is going to store that sum, that Taylor series. I'll call it result for simplicity, and we set it to 0, because then we're just going to keep adding on it. 0 plus something is that something. So it's nice to initialize to 0, because we can just keep adding on top of it. Then we will start adding terms, and we will use a loop. The best one is going to be, in this case, a while loop, as opposed to a for loop, because the while loop builds in a conditional, as I will demonstrate once we get the coding up and running. Okay, so a while loop will allow us to keep adding terms as long as our error, which is also going to be another variable that we need to measure as we add terms together. Okay, so and then this would be the formula x to the power n over n factorial as given up in the formula above. Check for convergence. So after we add each new term, we check the relative approximate error between the result with all of those terms minus the result, the previous result, right? So you're going to start with one term. The next one is going to be 2 terms. So the result with 2 terms minus the result with 1 term is going to give you your approximate error, okay? And then 3 terms minus 2 terms, and then 5 terms minus 4 terms, and so on, okay? To compute the relative error, you need to keep track of the previous sum. So we create a temporary variable to store that old result. And then if the relative error is less than or equal to the tolerance, then you can break the loop, okay? And then return the current sum, which is the approximation of e to the power x. And you can include error handling, like you have a negative, if the user provides a negative tolerance, you could throw an error, say, I cannot compute the negative tolerance. Send a positive tolerance or some non-numeric inputs. I'm not gonna touch on that. Okay, so let's get our Jupyter notebooks open, please, and we will work on this together. All right. So when you create a new notebook, you want to do file, new notebook, Python 3 kernel. You might have other kernels. I don't know why they get installed on the different computers. There's like a new computer coming up every year. Just choose a Python 3 kernel. Okay, it's the simplest one. That should give you all the libraries that we will need here. Okay. So every time I come to this lecture, there's like someone forgot some stuff. It's piling up really over here. So we should start keeping track of that. Okay. So I just created an empty notebook. And first thing I'm going to do is give it a name so I don't confuse myself. Next year, fall 2024, coding activity 4, Taylor series. Okay? And I'm going to zoom in for those in the back. Now, remember our boilerplate that I mentioned last time. So we can include, you can just copy and paste those boilerplates. Let me see, where did I have that file? Yeah, so, we had NumPy, import NumPy as MP. We're not going to use NumPy this time around in this example, because there's not going to be any arrays that we will need. But we will need, we can use NumPy if you want, or math. Import math. So math is a very basic module, but it only operates, the functions in the math module only operate on single value scalars, single value numbers. So you cannot call math.exponential on a NumPy array. Remember last time we applied the exponential or whatever function on an entire array? It will not work, the math.exponential will not work, but numpy.exponential will work on an array. So be careful. I'll show you example. Let's say x is an np.array, 0. Let's say for the sake of illustration, 0.5. Okay. If you were to do np.expx, it gives you an array of exponential 0.1, e to the 0.2, e to the 0.5. So you're using routines from the same library, right? But if you were to do math.exp on x, it's going to throw an error. Why? Because the exponential function that comes from the math module only operates on size 1 arrays. That's what this error is saying. Okay, so you can only apply it for a single value. Okay, so when you see these errors, don't freak out. It's probably you're just using the wrong function on an array or a single value where it's not accepted. Okay. Here in this case, I don't need NumPy in reality, so I can forgo that, but I'll just keep it here for the sake of keeping our boilerplate working. Okay. Now, why did I need math? Because math provides a factorial function. NumPy does not provide a factorial function. Okay, so if you were to do, I don't know if it does actually. So np, let's see, np dot. See, it doesn't have factorial. But math dot factorial, see, it has a factorial. Oh, how am I getting those things? Nobody asked. How am I getting these suggestions? Okay, so here's a trick. If I type math and I press period, and then if you press tab, it will give you access to all the subroutines inside a module or inside a submodule and so on. Okay? And then I type, you start typing, arctangent 8. Oh, look at that. I have atan, atan2, and hyperbolic arctangent. Or I want factorial, and I press tab, it will continue that. So press tab, then type factorial, you get that, okay? So that's one trick to get into what's inside a module or a submodule in Python, okay? All right, so we got our math, and the way I'm going to think about this is first I'm going to define my x value, which is, let's say, we want to evaluate the exponential at 2.5 or whatever value. And actually, let's define exponential Taylor series. And we said we wanted to take some value x and a tolerance tol. Okay? So now inside this subroutine, we have x. It's been passed to this subroutine, and a tolerance has been passed already. Okay? And like I said in the slides, I'm going to start by declaring a variable, an empty variable called result, and I'm going to initialize it to 0. Because then I'm going to use this result and just tag terms on top of it, okay? Keep adding terms on top of it, all right? And the idea here, I'm going to write this in pseudocode, okay? while my relative error, or while my error is less than as long as my error is greater than my tolerance. So the beauty of doing a while loop is that it builds a condition in your statement. So this is saying literally in English, as long as my error is greater than my tolerance, then keep doing whatever you want to do. Okay? Just think of it this way. Now, what is error? We haven't defined error yet. Error is going to be part of the loop because we need to compute it as we go along. Okay? But once you enter the loop, error has not been defined yet. So we need to give it an initial value. Okay? We need to give it an initial value. To make sure that we're entering that loop, the initial value of error must be greater than tolerance. It has to be greater than tolerance. So I can initialize my error to like 1e to the 5, just to make sure I enter the while loop. Okay? Or you can say it's tolerance plus 1e to the 5. Okay? Because what if they put a tolerance of 1e to the 5, which is ridiculous, right? That's where you need to do some error checking. Okay. Because the tolerance needs to be a small value or less than 100%. Okay, so now we have declared a variable error, a variable to store the error value. If you did the slides with the while loop, you understand kind of how the while loop works. Inside the while loop, we're going to have a calculation to update the value of the error. And as long as that error is greater than tolerance, the while loop is going to keep on running. Otherwise, it will just stop automatically. That's what's so great about the while loop. It's very efficient. It's the equivalent of a for loop and with an if statement inside it. So we could do a for loop and say add 1 billion terms, but stop. After we add each term, we can put an if statement and say check the error. If the error is less than tolerance, then break the for loop. It would be identical to this, except this is way more efficient because it is part of the Python language. It's going to be faster than breaking your for loop with an if statement. Remember, a while loop is a for loop with an if statement in it. Okay. And so, first thing I'm going to do is say my result. I'm going to augment my result. And you learned this plus equal. So I'm going to take my old result, okay, and I'm going to add on top of it 1 over math.factorial n. So if you, let me get the slides here. If you remember this formula here, right? This is the formula for the exponential. 1 over n factorial times x to the power n, okay? So I'm just going to write it. 1 over factorial n times x to the power n. So power is 2 stars and factorial. Okay, but we don't have n. What is n? It's the counter of terms, right? We're counting first term, second term, third term, and so on, okay? So n starts from 0. Based on the math formula, so we better start at 0. Simplest thing to do is put an n equals 0 over here, okay? And then over here, it's going to come in, n equals 0. That's going to be our first term. And then I need to augment n by 1. Because now we're ready to go to the next term, right? So we went in, n was equal 0. We added the first term. Now we need to augment n to go to the next one, okay? Now see how I'm building this? I'm building this kind of from the inside out, right? So put a variable here, put a variable there. I wrote 1 over factorial n x to the power n. I didn't know what n was, so I wrote it, but then I thought about what n needs to be. That's literally how I operate when I'm writing code in practice. It's rare to see someone just write code and for it to just work. If you're a human and you're thinking about it, right? Even ChatGPT thinks about it. You see, it pauses and like sometimes it erases what it wrote and then it adjusts it, right? Because it's kind of thinking along the way, right? So it's okay to think along the way. See how I'm building it from the inside out. The math is always my guide, okay? 1 over n factorial, x to the power n. Okay. Okay, great. Now, if we do this, and I do not recommend you do this because this is going to loop forever. Because error is always 10 to the 5 plus tolerance. So if you call this function now, it's going to crash your computer. Or you have to kill the kernel. Because we didn't update the value of error. Agreed? So now we need to update the value of error over here. We added the first term. We need to update the value of error so we see if we're making progress. Okay? Okay. So now, let's do that. My error is going to be the absolute value of, let's say, better approximation, and I'm writing this in pseudocode, better approximation minus worse approximation over better approximation. So let's put this all in parentheses, over better approximation. Okay. So what is going to be my better approximation? It's actually a result, because that's when we added this new term to it. That's going to be our most recent, most valuable approximation, the one with the most terms. Okay? So I'm going to actually put here result, and I'm going to divide this one by result. Okay? Now, what is the worst approximation? It's the old result, right? It's the one with one term less. So do we subtract one term? No, we don't subtract one term. We actually just store the old result in another variable. So once we go inside the loop, we have the opportunity. So think of result as a place in memory that's storing a value. We entered the loop. Result was 0. So technically, that's the old result. Then we updated it with some new information. So I have an opportunity here to say old result is equal result before I update it. Okay, let's say you go and update result, do this, and then go to the next step. Now, this one is the old result, and then we're going to update it again. So all you have to do here is say my old result or worse approximation is result. That's like so weird, but it's not, because you're programming, you're not writing math here. Technically, you're programming things. Think of it in terms of memory. We came into the loop. We had something in the location called result. So I'm going to store that in a temporary variable just because of this here. And then I'm going to update it. So then I take the updated minus the old. We finish the loop. We enter it again. We're going to take this one and store it as an old result and then update it. And then take the difference. See how that works? More terms minus less terms. Result minus old result. So this has to sink in, whether here in class or in the help sessions or after at home, ask questions. If this doesn't sink in, you're going to have a lot of trouble later. Did it sink in a little bit? Kind of, okay. When you're talking about it loudly, or with me or with the TAs, it will make sense. But when you go home, it doesn't. So get a mirror, or print our pictures, and put them in front of you and talk to us. Imagine you're talking to us. Talk about it loudly. Right? Old result equal new result, etc. Right? So talk about it. It will immediately make sense. And if not, then come and ask us. We'll talk to you. We'll talk with you about it, okay? All right, we're almost done. So now what's happening? Error is constantly being monitored by this while loop. So it goes this error. And then it comes here again and says, is error greater than tolerance? If it's still, then continue doing what you're doing. If not, just quit. Just leave the loop. It will automatically leave the loop. Okay? So now we computed our error. Do we want things in percentage or as a fraction? That's up to you to decide. Okay? And so let's say we want things to be in percentage. So I'm going to multiply this by 100. So tolerance here is going to come in as a percentage. So I'm going to put in a value 50 or 10 or 1. It's going to mean percent. Okay? It has to mean percent. Okay? And that's it. So here's what we're going to do now. Let's print some stuff because, you know, if you're in doubt, what should you do? Yes, thank you. Okay. So we're going to print. Let's try. I'm terrible with formatting printing stuff, but, you know, I'll try. Print n. I'm going to make a tab. And so this is going to track the number of terms. And then it's going to track the result. And then it's going to track the error. Okay? And I'm going to do a new line. Sorry, this should be a tab. So backslash t gives you a tab. Backslash n gives you a new line. And then just print this. Right? And then here we're going to print n for the number of terms that we've added. And that we've added to the Taylor series. Number of terms, and then we're going to add result and error in percentage, okay? This would be percent. Okay. Just error. All right. Okay, great. So now we defined this, but it's still missing something. We need to return something. Return result. Okay? Return result. All right, we ready? Okay, so let's see. Oops. Now, for the sake of illustration, I'm going to compute. So let's say x equal 2.5 and math.exponential of x. So what is it? So from the math module from Python, we get 12.1825. I don't trust all of these significant figures. Let's say we got first few. All right, so let's see what our formula does. EXP Taylor series of x, which is 2.5, right? And what tolerance? We said 1%. Okay? And let's run it and see what it does. Yay, okay. So the first term is 1, indeed, as in the Taylor series. It was 1 plus x squared over 2, and so on. And the error was 100%. Great, perfect. That's, we can't even define the error then. Then with 2 terms, the value became 3.5. And then the error was 71%. With 3 terms, the value became 6.625, and so on. We kept adding. With 8 terms, we got to 12.13. And the error was 0.99. Remember, our tolerance was 1%. So indeed, the while loop stopped once we got below 1%. That's what we told it to do. It's 12.13, not as close as the one coming from Python. So Python must be doing it to a tighter tolerance, to a smaller error. So let's try that. Maybe we go to 0.1% and see if we can beat Python. Okay, so we got to 12.179 with 10 terms. Still, Python is beating us, so let's go to an even smaller one. Okay, now we're getting 12.1823, and Python is doing 12.182, so I must have an even smaller error. Okay, so we're getting close, 1.824, right? So you see how we keep adding terms until we hit a desired tolerance, a desired error. So that you don't have to just madly add terms in your Taylor series. Okay? Now for this number, 2.5, we needed 14 terms. So I'm going to go back to 1% for simplicity. Okay? 1%. And we needed 8 terms to get to an error of 1%. Okay? But what if now I change my value of x? What if I go to 0.1? If you go to 0.1, look at that. With 3 terms, we only need 3 terms to get an error of 1%. Remember what I told you? I expect that we're going to need less terms for smaller values of x than larger values of x. And this is what's nice about this. For the same tolerance, the function, the routine automatically adjusts how many terms you need to add. So you don't just randomly keep adding terms arbitrarily and add more cost to your calculation. If x is larger, I think we're going to get, let's go to 10. We're going to do, look at that, 19 terms with e to the 10. Because those large numbers become harder to compute and keep track of. Right? You get x squared, 10 squared, 10 cubed, 10 to the 4th, and so on. They become larger and larger numbers, and there's more round off committed over there. Okay? In your homework, you're going to do the same thing. However, now, how do you choose your tolerance? Again, I don't know. In your homework, I show you a formula that ties the tolerance to the number of significant figures, which is something we understand fundamentally. Like the significant figures, the number of significant figures are the digits that we trust in a number. So then you can tell your routine, calculate e squared up to 4 significant figures. Internally, I want to do 4 significant figures. This is the formula that I need to get. This is the tolerance that I need to, and then do your thing. Okay? So it's an even better way of doing this calculation. Okay? Question? Okay. Great. And feel free to reuse the codes we write in class, build on them, augment them, make them better. Okay? That's totally fine. Pardon me?
Can you back up to the code?
Yeah. Tell me when to stop. This is recorded. You don't need to take pictures. This is recorded on YouTube. You can go find it on YouTube. Okay. But if you want to take pictures, take pictures. I don't care. Okay. So let's go back to the slides. All right. Let me move this guy. Okay, so I show you a couple of solutions here for this problem. Here's your summary: absolute, relative true error, absolute, relative approximate error. And again, current, previous approximation, or better, worse approximation. Think of it this way. All right? Those are the definitions of error. This is going to be, most of the time, what we will be using to assess the error in our numerical methods. Okay? Now it's time to talk about sources of errors, and I alluded to that early on. We're going to dig in a little bit deeper here, and I'll get the opportunity to also cover the Taylor series. Just out of curiosity, who's seen Taylor series at high school or sophomore levels? Okay. Did you understand anything about it? Oh, yeah. Okay. All right. So there's an advantage to seeing the same thing from a different perspective, or seeing it just again, because it will help anchor the ideas in your mind. So, happy to serve that role here. All right. So like we talked about early on, there are many sources of errors we deal with in engineering systems in science. There's modeling errors. Those are like really engineering type errors. You choose the wrong model for you're modeling a parachutist, diving in the air, or a flame engulfing a tank. For example, you choose the wrong model, wrong radiation, or an inadequate a model that doesn't really represent reality. So that would introduce an error compared to reality, right? And then in that case, you just change your model. You pick a different model, or you develop a better one. There are programming errors, mistakes in code, and numerical errors, which we are concerned with here. And there are primarily two, round-off and truncation errors. We briefly alluded to both. We're going to dig a little bit deeper today. Round-off errors, you saw that example with the Ariane 5 rocket. But here's a different summary of what round-off errors are. So anytime you add numbers on a computer, or a calculator, or a digital device, or even an abacus maybe, there is opportunity for round-off error. Always there's round-off error, actually, because real numbers have unlimited digits in them. And you cannot account for all of those digits, so you have to chop it off at some point. Chop off the number at some point, the calculation, and whatever you leave off are your round-off errors. Now, what's weird about this is like, well, how does this reflect on reality? Reality doesn't know that I'm chopping off a number. It does, because the systems we're trying to model, they represent reality. And if you chop off those numbers in your representation of reality, you're introducing more errors to your modeling of reality. There's already the modeling error. There's already some other coding errors, right? And then you add the computational round-off error, so you get in trouble. Now, think of the different digits in a number as occupying a spot in a computer's memory, or a bit, okay? So for example, a number like this one, and this is completely qualitative, just to illustrate how it works. We are not going to go into the details of digital representation of numbers and mantisas and whatnot. It's not the purpose of this discussion. It's just to let you think that a number like this is, think of it as occupying different bins in a computer memory, okay? And in fact, each one of those numbers, we're not representing them exactly as 1, 5, 4. We have to convert them to binary first, which I'll show next. But when there are less bits than there are significant figures or significant digits, the number is chopped or rounded. So when we talk about a computer, a 16-bit computer, 32-bit, 64-bit, the first computer I used, like in the 90s, had 8 bits. And it was so darn slow compared to today with like 64-bit computers and 128 bits. So it's just the size in your memory of how many digits you can store of a number. Okay, and so anytime you bypass the number of bits available in your memory, the number automatically gets chopped and the rest of the digits get discarded. So for example, in a 5-bit computer, you're only storing these significant figures and everything else is being chopped or rounded, depending on the computer, okay? Now, this rounding introduces an error called round-off error, which is the result. This is a definition of the inability of computers to represent all significant digits in a number. Is therefore the difference between the actual value of a number and its rounded representation that is actually on a computer. So that's the error you're committing there. Every time you add, multiply, subtract, every time you do an operation on numbers, you are guaranteed to have round-off errors. You always have round-off errors, unless you're working with integers and you have exact arithmetic there. That's a very special case. You can do exact arithmetic on integers without incurring any round-off error. 2 times 3 equals 6. 2 plus 2 equals 4. There's no round-off going on there. And specifically, if you tell Python or Mathematica or MathCAD or your calculator that we're doing operations on integers, okay? Now, obviously, the more bits you have, the more significant figures you can represent. Some common floating point, we call these, so when we declare variables in Python, real numbers are called floating point numbers for some reason, okay? It's just real numbers, okay? It's just real numbers. Now, even on a 32-bit computer, you can trick the code to store a 64-bit number. It just makes up extra memory and keeps track of all the digits. You can store a 256-bit number. You can do that. It just gets a little bit more complicated from the code's perspective, but it can be done with modern codes, and it's actually an example we're going to do next. So typically what you'll see when you declare variables in programming, MATLAB, C++, Java, Python, you have 16-bit floating point numbers, 32-bit, 64-bit, or 128-bit, or 256, okay? And so those refer to how many significant figures or how many digits can you keep track in a number. Typically, Python defaults to 64 bits for floats. So you have 64 spots in memory to represent a number. Okay? First, the number is converted to binary, which is in reality what happens. And with binary, you get many more digits than the real number itself. And those are the numbers, the digits that are stored in memory. Because computers are binary, it's a transistor state, 0 or 1. Okay? Either it's charged or not, right? And so you got just these states in the computer memory. OK, so now here's this really cool example that we're going to do together. We're going to take the number 10 to the minus 5, okay, 1e to the minus 5, and we're going to add it in a for loop 100,000 times. So 100,000 times 10 to the minus 5 is exactly 1. That's what the math tells us, correct? So the exact value here should be, if you add 10 to the minus 5 100,000 times, or 10 to the 5 times, the result should be 1, right? 10 to the minus 5 times 10 to the 5 is 1. Now we're going to do this addition using 16, 32, 64, and 128-bit precision floats in Python, and we're going to compare the results of each one of those. Okay? So this is we're never going to be using this, but this is just for illustration purposes to show you how different precisions in numbers can result in different answers. Okay, but in practice, we're never using these, whatever you're going to see here. This is just for illustration purposes. Okay. So now there's one more thing that I need to mention, is that 16-bit precision is usually referred to as half precision. 32-bit is single precision, double precision for 64-bit, quadruple precision for 128-bit, and so on. Okay? So those are the names. All right. So here's how we're going to do this. We will define the number 10 to the minus 5. Just put in a variable. So this will default to a 64-bit floating point, and which is fine. It's just a value in there. And then we define the true value to be 1. That's we know the true answer in this case. 10 to the minus 5 times 10 to the 5 is 1. Then we will declare different variables, different types in Python, which you could do with NumPy. If I call NumPy float 16 and say 10 to the minus 5, is going to take 1e to the minus 5 and represent it in a 16-bit register. Okay? So internally, if 10 to the minus 5 needs 500 bits to be represented, it's going to chop off all of those remaining bits. Same thing for single precision or 32 bits, same thing for 64, same thing for 128. But what's cool about NumPy is it allows you to represent higher precision numbers or lower precision numbers on our 64-bit computers. Okay, so it does that internally. It's a great way to illustrate things. All right. So we're going to declare different variables, a single precision variable, a half precision single, double, and quadruple precision. Okay, and so we're going to, for each one of those, we're going to do a for loop and add that number. We're going to add all the 16-bit numbers, all the 32-bit numbers, et cetera, and see what results we're going to get. So what do you think we're going to get? Which one is going to be the closest to 1? 128 bits, 64 bits, 32 bits. Pardon me? Yeah, 128. The worst one is going to be 64 bits. Worst is going to be 32. The worst one is going to be 16 bits. Okay. Then we're going to add all of those numbers in a for loop, and then we're going to compare the result. All right? So let's go on our Jupyter notebooks. And this is coding activity 5. So here's what I'm going to do here. I'll show you. File, new notebook, Python 3. OK? And I'm going to call this Fall 2024 coding activity 5. Adding 1e to the minus 5, okay, with different precisions. All right. So definitely, I'm going to need NumPy for this one, right? So that I'm able to do the 16-bit, 64, and 128, and so on and so forth, right? All right. So let's see. So import NumPy as MP, okay? And then I'm going to declare those variables. X half is equal mp.float 16, 1e to the minus 5. Oops. So this is half precision representation of 1e to the minus 5, okay? And then X single precision is mp.float 32, 1e to the minus 5. And again, this would be single precision. X double precision is mp.float 64. So that's a 64-bit representation of 1e to the minus 5. Again, think of this as 1e to the minus 5 is a number that has a lot of binary digits. I don't know how many. But we're only going to store, we're only going to take the first 16 bits of that number, or the first 32 bits, or the digits of that binary value. Now, when you convert back to float, to real space, it's not going to be 10 to the minus 5. So you're really not adding 10 to the minus 5 in any one of those variables. Okay. X double and X quadruple, quad precision, mp.float 128, 1e to the minus 5. Okay? Now, we're going to store the summation in results that are of the appropriate precision as well. So to be truly correct, you want to store the result of the 16-bit addition in a 16-bit result, not in a 64-bit result. You have to be very precise about this to get the answer properly. So we will do result with half precision is np.float 16. Just initialize it to 0. Result with single precision is mp.float 32. Result double precision is mp.float 64. So I'm just initializing a result variable. It should be 0 because I'm going to add terms to it like we did with the Taylor series. But now I'm being a little more specific. I want my result variable to be consistent with the precision of the value we're adding. When we're adding 16-bit numbers, I'm going to store them in a 16-bit result. Okay? When we're adding 64-bit numbers, I'm going to store them in 64-bit result. That's what I'm declaring here. And then result quad precision, mp.float 128, 0.0. Again, we will never use these ever again. Okay? This is just to demonstrate how things can behave interestingly with round-off errors. All right. So now we can run our for loop. Let's run our for loop. For I in range, we're going to do a range to 100,000. Okay, so 1, 2, 3, 4, 5 zeros. Okay. So I is going to go from 0 to 9999999. Okay? So it's 100,000 times. And then we will say result half plus equal x half. Result double or single plus equal x single. Result double plus equal x double, and result quad plus equal x quad. Okay? Fine? Just adding 100, we're adding x half 100,000 times, x single 100,000 times, x double 100,000 times, and x quad 100,000 times. Okay? All right? So you can print the number now or report an error. Let's say we're just going to print the number. So let's say 16-bit result was equal to result half, copy paste, 32-bit, 64-bit, and 128-bit result. So this will be result single. And notice how I press tab to autocomplete the word. Result single, result double, I type D, and I press tab, it automatically completes it. And this is quad, I press Q and press tab. Okay. So once you got this, run it. And let's see what you got. Anybody in the back got it? Can you guys put your names in front, please? Name tags, yeah. Anybody has an answer? All right, Alexandra? Pardon me? Oh. This specifically. Maybe on your computer, it's not allowing that. So comment that out, okay? And go up to 64, okay? Maybe my computer is 128 bits, I don't know. And this one, 64. So if you're getting an error that you can't get to 128 bits, just comment those pieces out. Are you done? Did you get an answer? Okay. Anybody get an answer? Yeah? Gretchen?
Yeah.
What? Is it 1?
It's not exactly 1.
Uh-huh.
It seems to be a closer approximation.
Is the 128-bit closer?
Well, I can't put that one, but
The 64-bit is closer than the other ones?
it's lower to expect.
Okay. What did you get? Did you go to up to 128?
I got up to 64.
Okay. Okay. All right. So let's see what I got here. When I run this, okay, with the 16-bit result, it's horrible. 0.03. Is that what you got? Yeah. That's so far away from 1. Like imagine you're just adding 10 to the minus 5 100,000 times. So now consider this. What if you have a clock that's running satellite? Your satellite is calculating something. Hundreds of thousands of or millions of seconds orbiting. And it has an error and it's accumulating. It's a small error for one calculation. 16-bit 10 to the minus 5 minus 10 to the minus 5 is not that big. But once you accumulate that error, it becomes very large. Now, once you go to 32 bits, you get a little bit larger than 1. 64-bit is closer to 1. 128 is actually closer. Now, how do we quantify that? We need to measure and to compute the true error. So in this case, we would be able to compute the true error, okay, because we know the true value, and it's 1. So you can add that calculation, and you will show that 128-bit, you get an error of like 10 to the minus 12% or so. So we can do that here if you want, but let me see. Yeah, so on my results, if I do this, so what I get is with the 16-bit, the error is 96%. 32-bit, the error is 0.1%. 64-bit is 10 to the minus 10%, and 128 bits is 10 to the minus 13 bits, 13%. So indeed, the more precision, the more bits you have, the better accuracy, the better precision you have to get to the true value, but you still have a round-off error. You cannot avoid it. Okay, it is always there. All right, so let's see now how round-off error can actually be a big deal. Okay, so round-off errors in real life, though this is a real problem. First, you saw the Ariane 5 rocket explosion. So that's a true real-life situation that was devastating. Another one that's quite popular is the Scud missile defense array in the 1990s. An incident occurred in one of the bases in Iraq. So this is lifted out of Wikipedia. It's the Patriot missile disaster. So the Patriot missile system is a defense system that consists of defensive rockets with a radar that's constantly scanning the sky, or multiple radars. They're constantly scanning the sky for potential missiles that are trying to target the military base or a civilian installation or whatnot, okay? And once the missile detects a bird, it says like, no, this is a bird, we're not going to shoot it down, right? But if it detects a very high-speed object, and if it can tell that the object is actually headed towards us through multiple pulses of the radar, sends the radar pulse first time, second time, like, oh no, this is actually getting closer and it's really fast. Let's deploy then our rocket batteries. It will deploy those rockets to shoot it down, okay? So you can actually go on YouTube, see examples of how it operates. You can also search for Iron Dome. That's a similar system that does that, shoots missiles up in the sky. Okay, now the disaster occurred. So this is a picture of one of the batteries in the field being deployed. So on February 25, 1991, an Iraqi Scud missile hit the barracks in Dhahran, Saudi Arabia. So in Saudi Arabia, the US had a military base in Dhahran, and they're operating over there. And an Iraqi Scud was, they would always shoot Scud missiles, but they get intercepted, except on that day, and it killed 28 soldiers. And you can read that, but the point is, there was a 24-bit. There was a translation in the clock. So let's read it. Government investigation revealed that the failed intercept at Dhahran had been caused by a software error in the system's handling of timestamps. Okay, so there's an internal clock in the system. Once you turn on the battery, the rocket battery and the radar, there's an internal clock that starts clicking. Why do we need the clock? To be able to measure the time between the different pulses of the radar. You send one pulse, comes back, and then you send another pulse, there's an object. The difference in time can tell you a lot about the speed of the object and where it's located. Okay? So that's very important. If your clock is messed up, then the location of the missile is going to be messed up as well. And this is exactly what happened. The Patriot missile had been in operation for 100 hours. So 100 hours times 60 minutes per hour times 60 seconds per minute times, each second it had a ticking clock of 10 cycles times 10. So you get over 1 million clicks for that clock, okay, operating. So think of the 100,000 number that we added. So turns out there was a small error, very, very, very small error in the clock, because of a conversion from 48-bit to 24-bit precision. Okay, the radar system had successfully detected the Scud missile and predicted where to look for it next. However, the timestamp of the two radar pulses were converted to floating point differently. One correctly, and the other introducing an error proportional to the 100 hours, which was a conversion from a 48-bit number to a 24-bit number. And over 100 hours times minutes, times seconds, times clocks per second, cycles per second, That ended up being a very large error. Okay, and then the timestamp, so it sent the first timestamp. The second timestamp came, the error was about 4 seconds. And that told the battery, oh no, the rocket the Scud missile is out of range. Okay, so don't shoot, don't intercept, and then it unfortunately hit them, and the disaster happened. Now, this used to be a homework problem. This year we didn't have time to do it, but anyway, it's a real story. So don't mess with round-off errors. Don't do foolish conversions from one significant figures to another. So I want you to worry about this a little bit. Not too much, okay? We can do engineering very, very well. These are the black swans, the black swan events, okay? They're bound to happen. Just don't be one of those statistics being involved in one of those things, okay? Don't make foolish conversions from integers to floating points, etc. Be critical and think clearly about the numbers that you're using. There are other ones, the Ariane 5, the Vancouver Stock Exchange. That's a hilarious story. It's sad. A lot of people lost a lot of money because it just dropped the, how you hear like the Dow Jones or the S&P 500 is at 21,782. It off 3 significant figures from that number, which messed up with the returns on the stock exchange. It crashed the entire stock exchange. Okay, so all right. Anyway, you can see more of these disasters at this website. Okay. Should you worry? Yes, a little bit, but not really, because most engineering and mathematical systems will cancel out the error or wash it away. Like the problems we deal with mostly in chemical engineers, these kinds of errors tend to be washed away by what we call diffusion in the problem, heat and mass transfer, etc. So you cannot tend to hide it. But once you deal with data and data analysis, that's where you might end up in trouble. So be careful about that. Don't let it slow you down, okay? And don't blindly trust numbers just because the computer gave them to you. All right, so I have about 15 minutes left. No break, sorry. I'm trying to complete this today. It might spill over a little bit for Thursday, but I want to talk about truncation error. So that's round-off error, right? Hopefully I've convinced you not to trust numbers on your computer and go do fun tricks with your friends or your colleagues, like add the number 10 to the minus 5, 10 to the minus 6, 1 million times, right? And you're going to get a big error there. So it's not going to be 1. Okay. So truncation error is the result, this is the definition in gray, is the result of truncating an exact mathematical expression for the purposes of computer or numerical implementation. It's a very simple definition. The math is done exactly on paper, pen and paper, or even with math software. You have usually infinite series representations, exact integrals. Those symbols have exact meaning in them. Once we put them on a computer, we have to chop them up, we have to truncate them, because we cannot add, again, the Taylor series is a great example. We cannot add an infinite amount of numbers. You'll have a formula that goes forever. So you have to stop somewhere. Where you stop, that defines your approximation. What you neglect, that defines your truncation error. Because that gives you the definition between the truth, the mathematical truth, which has a symbol in it, and what you did numerically. Now, be careful. If you're reading, you might be reading an article that's written by a computer scientist or computer science. You're Googling something about this course, and some computer scientist is writing about this. In computer science, round-off error, they also call it truncation error. Okay, because they're truncating the number. Understandable. Here we're trying to adhere strictly to the mathematical definition. So we'll call the numbers one just round-off. Errors when you cannot represent numbers exactly. Truncation error is strictly to exact mathematical formulas, exact mathematical symbols. This has to do with the symbolic form of your formula. Whatever you truncate, that's going to define your truncation error. Okay, so now we'll go back to the Taylor series. And we're going to revisit the Taylor series over and over again in this course because it's very fundamental to numerical methods. We will start with this standard definition. The Taylor theorem states that for some function f of x, it is going to be continuous. Don't worry about that. Just means that this function is nice and continues everywhere. There's no sudden change. It's not piecewise continuous like 0 here and 1 over there. It's always nice and continuous together, okay? And so for a continuous function whose derivatives are also continuous, so you can keep taking derivatives. They might be 0, but then you can keep taking derivatives. As compared to a piecewise continuous function, like a step function, you cannot define the derivative at the point where they're connected together. Like you have a function that's 0 and then suddenly 1. What is the derivative at that point in between? It's undefined, okay? So we don't deal with those functions for Taylor series, all right? When the derivatives are also continuous, then you can say that this function at any point x in the vicinity of some number a, and I'll explain I'll define the formula and then I'll explain what it means. Then you can express that function at that point x in terms of everything known about a. So think of it this way. If you know the value of some quantity at point A, you know its derivative, first derivative, second, third. If you know everything about that function, you don't know what the function is, but you know its value and its derivatives at point A, you can predict the function at any neighboring point close to A. So you look at the right-hand side here, you know f of A, you know f prime of A, you know f double prime of A, and so on. And x is the value that you want to predict the function at. So you know what the value x is. Then you can compute f of x in terms of everything you know about the function at A. Okay? So that's the power of Taylor series, that if you know the function and its derivative at some value, you can predict the value of the function in the neighborhood of that value. Okay? So in other words, we say that the Taylor series of f of x in the vicinity of A is this formula. It's a simple polynomial. Because fa, f prime of a, f double prime, they're just numbers. And x, a is a number. X minus a is becomes so x squared, x cubed, and so on. So it converts the function to a polynomial. And that's very powerful. That's what allowed us to compute the exponential and the sign in terms of elementary operations, multiplications and additions. Okay? We usually say that this is the Taylor series of f of x around A or in the vicinity of A. Okay. So for example, the Taylor series of f of x equal e to the x in the vicinity of 0. So A is equal to 0. So it become e to the 0 plus e prime at 0, which is e to the 0 because the derivative of the exponential is itself, right? And so on and so forth. And that's where you get this polynomial. Formula for the exponential is nothing more than the Taylor series of the exponential in the vicinity of 0. Okay? So now here's your activity. Grab a pen and paper. Now I want you to write the Taylor series of the exponential in the vicinity of 1. Just an exercise. So A is equal to 1 right now. Just write me the formula. Write a few terms. Like first 3 terms. Just do 3 terms, 4 terms, 3 terms. Write it in symbolic form. The exponential, the derivative, first, second, third, fourth, they're all e to the x, okay? So f prime is e to the x, f double prime is e to the x, and so on. Let's see, we got some answers. Start calling people. Okay, so with the first term, it's e to the 1. So how did you get that?
You plug in a
Equal 1, okay. Okay, what's the second term? Let's see, someone else. So we got the first term, okay. Okay, because f prime is e to the x. At a, it's e to the 1 times x minus 1. What's, Alexandra? Yep. Yep. Okay. So you got it. So it's simple plug and play, right? So you just simply substitute a equal 1 and just evaluate those terms. So you get e plus e x minus 1, et cetera, et cetera. Okay, I don't have much time to dig deeper into this, but I want now to ask a question. What is the difference between this series in the vicinity of 1 and the series in the vicinity of 0? On the left-hand side, both of them are e to the x. So they should be equal, right? But what's the advantage of this one, and what's the advantage of the other one? What do you think? Yes?
Something to do with like having the value of in the equation versus not in the.
Sure, that could be, yep, because this, so your colleague is saying, this is a great answer, actually. I hadn't thought of that. There's a little more computational issues here because there's E, and you need to compute E. But suppose you know the value of E, 2.781. You just put it in there. So suppose you know that. You had an answer? Ah. Okay. So, but can I use the other one to get values closer to 1? Or you will need more terms for the same error. Okay. All right. So what your colleague is saying, well, I can't read your name. It's like the smallest font. Okay. So what your colleague is saying, thank you. So what your colleague is saying is that the answer is kind of in the given. This is the Taylor series of the exponential in the vicinity of 1. The other one was the Taylor series of the exponential in the vicinity of 0. So when we take this formula and try to calculate e to the x, and x is close to 1, we're going to get more accurate with this formula than the other one. Or specifically, we will need less terms to get to the same accuracy than with the other formula. Both formulas will be equal with an infinite number of terms for any x. Okay, for pick a value of x, both of them will be equal with an infinite number of terms. But for the same tolerance, this one will require less terms than the other one because it's developed in the vicinity of 1. If you choose a value close to 0, the other one will be better. Now, we always use the other one because it's just simple and easy and clean, right? But you can use any Taylor series in the vicinity of whatever you want and apply it to any other number. You just need to add more terms. On Thursday, I will show you the effect of how, as you add more terms, you get more and more accurate everywhere in the space. Okay? All right, I'll see you on Thursday. Thank you.